Similarity transformations, otherwise called similitude, was introduced in the further math syllabus in the year 2019. Since then, yeah, it has featured in all the further math paper 2 exam questions, that is 2019, 2020, 2021 and 2022, as well as in regional mocks and in school exams. So the maximum mark that this question always carries is 9 marks and the minimum mark is 8 marks. Now, knowing that further math paper 2 carries 50% of further math, it means scoring 9 points or 8 points, for example, it means automatically you get a 4.5% of the whole examination or a 4% of the whole examination. So all students are advised to complete this video and secure their 9 points in paper 2, because all you need to know is the basic application of complex numbers. That's all you need to know. So let's get started with what we have for you today. Alright, so not to give you much details, because there are already 2 videos in this channel that is talking about this topic. The first video was talking about the topic in like a brief review about the topic, where I made mention of the various transformations that do exist, where we had homothesis, we had rotations, we had translations, and then we had compositions of these to give us similitude. So in this video we are going to base ourselves on similitude, and we are just going to be looking at 6 common things or 6 parameters or 6 important things that we need to know about similitude. So they are already highlighted to you, and you have a practice problem as well, which we are going to practice on. So the first thing we need to know the angle of rotation of a similitude. In fact, a similarity transformation, as we said, a similitude is a transformation that maps points from, let's say, the point Z is mapped onto the point Z prime. Z is a point and Z prime is the image, and the complex representation of all such transformations is given by the equation Z prime is equal to alpha Z plus beta, where alpha and beta are complex numbers. Okay, so these are the 6 different parameters that we have to know about these similarity transformations. The first is the angle of rotation, the second is a scale factor, the third is the center of the transformation, the fourth is the image of any point whose affix is Z, the fifth is showing that it is actually a similarity transformation, that is a similitude, and the sixth is giving the geometric interpretation of that transformation. So according to this practice problem, which we are going to do only this practice problem in this video, we have 4 things, and this is actually a practice problem that was given in the Etokebe mock examination of 2023. So the equation reads f of z is equal to z prime equal to 2z plus 3 minus 4i. It's actually a transformation. Okay, so we have 4 questions that follow that transformation. The first thing is we should find the image of the affix z equal to 2 minus I. The second is that we should determine the affix of the invariant point of f. The third is that we should show that f is a similarity transformation, stating its radius. And finally, we should give the geometric interpretation of our results, or the geometric interpretation of f. Alright, so there are some key terms that we need to know their definition. Something like affix. What is an affix? The affix of a point is simply the complex number representing the point. So the affix is a complex number. So when they say find the image of this affix, you see the affix is written as a complex number. So if I give you a point and I say write me the affix, you need to write the complex number that represents that point. Now I think that is the only unusual, that is unused word, but the rest of the words are okay. Okay, so let us begin with the first part. That's question 1. How do we get the image of the affix z equal to 2 minus I? Remember that z prime is simply f of z. You see that the complex function on the right hand side is 2z plus 3 minus 4i. This z here is a complex number, so I can just call 2z plus 3 minus 4i to be a function of z, which is f of z, and it is the image of the point z. Okay, so to get the image of z equal to 2 minus I need to come to my complex number here. Z prime is the image of any z, and I replaced the z here with 2 minus I. So z prime is equal to 2 into 2 minus I plus 3 minus 4i. You get a method mark for that. You simplify and then you get your answer map. Now the second question, and like I said, you have to always put your answer in a box. It all depends on you, but it is preferable and more presentable to always highlight that this is your final answer, meaning you try to put it in a box so your work is going to be neat. Now for the second question, we need to determine the affix of the invariant point. Okay, so the affix of the invariant point is simply the complex number that represents the invariant point, because the invariant point is a point, but we getting the affix means we should get that complex number that represents that point. Anyways, you are going to get both of them, so you better understand the difference between the affix and a point, or the affix of a point and the point itself. So the first thing to note is that the invariant point is a point that remains unchanged when that is, the point is mapped onto itself. So it means that, let's just say for example that the invariant point of this transformation f is zi. Okay, now what does this follow? It follows that whenever I impute zi into my transformation, the image is going to give me the zi itself, meaning that via the transformation the point remains unchanged, so the point is mapped onto itself. So f of zi equal to zi. Okay, it therefore means that our z prime of I actually is equal to z of I, because z prime is the image of z, but since that z prime is, since we are dealing with the invariant point, then the image is equal to the point. Now the image being equal to the point, it means I just need to replace z prime here with zi. I come to this and I replace z here with zi. Okay, and we equate the two. You get a method mark for that. We now simplify to get zi. You get an answer map. Okay, now remember that we were finding the affix of the invariant point, so it should give us a complex number because we need the affix. If they ask you to find the invariant point, you first of all get the affix and then you state the point. Okay, now every point is represented. Let's take the general point x plus iy. Now if you want to represent it, let's take the general complex number x plus iy. If you want to represent it as a point, it's going to be the point x comma y. So you take the real part and then you take the imaginary part. So it means here, if you were asked to determine the invariant point, your answer is supposed to be as a point. You first of all start by determining the affix of that invariant point. In this case, it is negative 3 plus 4i. Then you write it as a point, which is negative 3, 4. You get your answer map. Alright, the third question is asking us to show that this transformation f is a similarity transformation or a similitude stating its radius. So what I explained in one of the videos, which I'm going to include the link of that video in the description of this video so that you can click and watch. I explain what is meant to be by a similarity transformation. It is simply a transformation such that if you're taking 2 points, for example, if I have let's just say we have, for example, we have a square. Okay, this is my square, and then I pass this square through this transformation here. The transformation is f. Now if this transformation is a similarity transformation, then I am going to get a new square. Okay, I'm going to get a new square, and let's just say this is a, this is b. For example, let me just choose 2 points on this square. This is a, this is b, this is a prime, the image of a, and then this is b prime. Okay, the image of B. Now if this f here is a similarity transformation, it therefore means that the distance between the images of these points, so the distance between the images of the points, that is the image of A prime, the image of A and the image of B, that distance is A prime B prime, then it is equal to a scalar multiple of the distance between the 2 points. Okay, so a scalar multiple of the distance between the 2 points. The distance between the 2 points is AB. So if this happens, then we say that the transformation F is a similarity transformation. So how then do we prove that it is a similarity transformation? In fact, this K here is what we call the scale factor or the radius. So either I call it the scale factor or you call it the radius. So follow keenly how the various steps that you use, the various statements that you make to actually prove that this given transformation here is a similarity transformation. Alright, so the first thing to do is that we are going to consider some arbitrary points on the plane and also their images. So we are going to consider the point A prime, where the image of A is A prime, and then we have the point B and B prime, where the image of B is B prime on the plane. But since the plane is a complex plane, then we need the affixes of these points. We don't need the points, we need their affixes. So the affix of A, remember I said the affix of a point is a complex number representing a point, and generally when you see Z, Z is simply a complex number that is in a generic case. So the affix of A will be ZA, the affix of A prime will be ZA prime. Same thing goes for B and same thing goes for B prime. So we consider these points on a complex plane, and since they are in this complex plane, it means that whenever I impute the complex number A into my transformation, I get the image which is ZA prime, and the same thing goes for the complex number B. When you impute the complex number B into your transformation, you receive that the output becomes the image of B, which is ZB prime. Okay, now we are going to form two different equations. For the first equation, I just need to come here and I replace Z prime with ZA prime because it is the image of A. But instead of putting Z here, I'm going to put ZA because ZA is the affix of the point A, while ZA prime is the affix of the image of the point A. So you replace ZA prime with Z prime, and then you replace Z prime with ZA prime, and you replace Z with ZA. That's your first equation. You do the same thing for B, and then since you need the distance between the images of the points, remember that when I wrote something like the distance between the images of the point, that is A prime B prime, and I need to put a distance, should be equal to a scalar multiple, which is K, times the distance between the points. Okay, if you want to write it as a complex number, you know that A prime B prime, if you want to get the distance between A prime B prime, you just need to take the difference between the complex number representing those points, and then you take the modulus, because the modulus of the complex number is simply its length. That's the length of a complex number. That is why if I give you a complex number, for example, let's just say 2 plus I, for example, and I give you another complex number, maybe 3 minus I, and I say find the distance between these two complex numbers, you need to take the difference between the complex numbers and then you take the modulus. It gives you the distance. Okay, so since we need that distance, it means we need to that distance from the images, we need a distance between the images of the points, I mean the distance between the points as well. So the distance between the images of the points, let's just take equation 1. So doing this like you have your method mark, which is 1 mark. Now if you take equation 1 minus equation 2, okay, equation star minus equation star star, here you're going on the left hand side, you have ZA prime minus ZB prime. Okay, we have ZA prime minus ZB prime. You see that this 3 minus 4i cancels because it is the same in both equations, and then we have 2ZA minus 2ZB, which is 2 into ZA minus ZB. we are not done. Why are we not done? Because we need the distance between the images of the points and the distance between the points themselves. At this level, we are still dealing with complex numbers. So to get that distance, we need to take the absolute value, that's the modulus on both sides. Sorry, we need to take the modulus on both sides, because taking the modulus of a complex number is simply a distance. Okay, so the modulus of, because za prime minus zb prime is still a complex number, now the modulus gives us the distance between the 2 points. So if we take the modulus on both sides, we have the modulus of the left hand side to be equal to, now the modulus of 2 is 2 because 2 is already real, then times the modulus of za minus zb. This gives you another method map. So we clearly see that we can conclude that f is a similarity transformation or a similitude with radius k equal to 2. This is a radius because on the left hand side is the distance between the images of the points equal to k, which is 2, times the distance between the points. So concluding like this, you get your answer map. Okay, now let us proceed to the last question, which is asking us to give the geometric interpretation of our results. Okay, so what is, first of all, a similitude? A similitude is actually a transformation that is gotten as a result of composition of some other transformations. Okay, so sometimes you can, to get a similitude, we compose a homotety and a translation, and also maybe sometimes a rotation. Okay, so geometrically, what is a similitude? Now, a homotety is what we call an enlargement or a reduction. If it's an enlargement, if the scale factor or the radius of the complex transformation is greater than 1, we call it an enlargement. If it is less than 1 but greater than 0, we call it a reduction. Okay, so in this case, we see that this similitude is actually an enlargement because the scale factor is greater than 1, as the scale factor is 2, or we call it the radius. It all depends on how you want to name it. So since our k is greater than 2, then it is first of all an enlargement. Okay, then it is followed by a translation about the vector of this complex number, because it's a complex number, and that is simply the translation vector, where we are going to write it as a vector, because 3 minus 4i is a complex number. This I here is a complex number, but writing it as a vector, we need to write the x component, we multiply it with the unit vector in the x direction, plus the y component, we multiply it with the unit vector in the y direction. So in the vectors, you have I and j. Those I and j are unit vectors. But in the complex number, this I here is not a vector, it is a complex number. So don't get confused between the I in vector and the I in complex numbers. The I in vectors is a unit vector, meaning a vector whose magnitude is 1, and then the I in complex numbers is simply the complex number I. Okay, so our f here is an enlargement, but you don't end there. You need to give the characteristic of that enlargement. So an enlargement of radius k equal to 2, you get the first answer map, then followed by a translation, but you need to give a characteristic of that translation. So you give the translation vector, it is 3i minus 4j. 3i because 3 is the real component of my complex number, then we need to attach it with the unit vector in that direction. Then negative 4 is the imaginary part of that complex number, which is simply the y component, but we need to attach the j to it to show that that is, because j is a unit vector in the vertical direction. So doing this, you get the next answer map. Like I said, for those of you who never watched the first video about these complex transformations, endeavor to watch that video so you get a brief review about what homotheties are, what rotations are, what translations are, and all the rest. Okay, so I'm going to bring your attention into some other things here, because according to our 6 parameters that we're looking at, we have seen the scale factor. The scale factor is simply the radius. We have not seen the center. We have seen the image. We have seen the proof of showing that F is a similarity transformation, and we have seen the geometric interpretation of our results. Now, what about the angle of rotation, and what about the scale factor, and what about okay, we have seen the scale factor. What about the center of the transformation? Okay, so I'm going to talk about the angle of rotation, the scale factor, and the center of the transformation. So I'm going to give you shortcuts on how to find them whenever you're given complex transformations of these forms of this form and you're told that it's a similitude. So the first thing to do is the angle of rotation is the argument of the complex number alpha. So like I told you guys in the beginning that you just need to apply complex numbers here. There is no big deal. You just need to apply complex numbers. So the angle of rotation is the argument of the complex number alpha. So if you can find the argument of any complex number, then you can get the angle of rotation of this similitude. The scale factor is the modulus of the complex number alpha still. So the scale factor is the modulus. So if you come here, you see that your alpha is 2, okay, and since 2 is already real, then the modulus is 2. Your beta is 3 minus 4i. In fact, if we want to find the scale factor here, not by going through this long step that is a radius as well, not by going through this long step, we can just say our scale factor is the modulus of the complex number alpha, and our complex number alpha here is 2. Remember that 2 is a complex number whose imaginary part is 0. The biggest set is the set of complex numbers because the set of real numbers belongs to the set of complex numbers. So all real numbers are complex numbers with 0 imaginary part. So 2 is a complex number, but the imaginary part is 0 because we write it as 2 plus 0i. So the scale factor is the modulus of 2, which is 2 because it is actually real. What about the argument, the angle of rotation? It is the argument of alpha, which is the argument of 2. Okay, since 2 is positive, and we know that for us to get the argument of a complex number, we plot the complex number, identify the quadrant, and then we take the respective angle. But the complex number here is 2, and 2 is a real part, so the imaginary part is 0. So if you want to plot the complex number 2, it's just going to be the point in the Argand diagram is going to be 2 0, and it's going to be 2 0, yes, and 2 0 lies on the x-axis, so the argument is supposed to be 0, not pi on 2. Sorry for that error. So the argument here is supposed to be 0, okay, not pi on 2, because the point 2 0 lies on the x-axis, and the argument of a complex number is the angle that the complex number makes to the positive x-axis. Since it already lies on that x-axis, it means it makes no angle with that axis. Okay, so the argument is 0. And finally, like I said, the center of the transformation. The center of the transformation is also the invariant point, because the center of the transformation is the only point which, when the transformation takes place, it remains unchanged. So getting the invariant point is equivalent to getting the center of the transformation. In some questions, they will tell you to get the invariant point, hence state the center of the transformation. Okay, so like in this case, if they say what's the center of our transformation, it's going to be the point -3, 4, because it is the invariant point. Okay, and I think that is all for the video. Now stay tuned to the next part of this similarity transformation videos, that is video part 2, because in that video I'm going to talk about 4 things. The first thing is, how can we compose 2 similitudes? It means if you compose 2 similitudes, what are we going to get? What are going to be the properties of the new transformation that we have? The next, how can we get the Cartesian equation of a similitude? The next is, how can we get the inverse of a similitude? And the fourth, we are going to talk about indirect similitude. So all we have been talking about here is direct similitude. Okay, so in the next video, if the video is too lengthy, maybe I might push indirect similitude to the 3rd video, but these are the things that I'm going to explain for you before you write your GC examination. Stay tuned for more videos. Thank you for watching. subscribe to the channel, turn on your notifications so that whenever videos are uploaded, you always be notified to come and watch.